Long ago, in primitive times, the only way men could get water was by dipping it from a passing stream. After a while, they dug wells, and this was an improvement because then people didn't have to live right on the bank of the stream, and also the well water was often less contaminated than that which flowed in a river or creek. But it was still a long way from what we enjoy today. Then came the windmill, an improvement because it lifted water from the well without hand labor and placed it in a tank. Now, for the first time, water could be piped inside the house. In these modern times, we have gone to the high mountains, more than 100 miles away, where each winter, nature stores a vast supply of water in the form of snow. Here on the western slope of the Sierra Nevada range, our water supply originates. The summit of this range is a little more than 10,000 feet above sea level. The watershed, which empties into the Mokelumne River, covers 575 square miles. Every flake of snow which falls in this great uninhabited region must eventually melt and flow into the river and finally be captured for our use at Pardee Reservoir. These great white banks are really nature's way of storing an immense quantity of water, which only awaits the warming touch of the spring sun to turn it into the element so important to our lives. The amount of snow which falls varies considerably from year to year, but the utility district needs to know in advance what the water harvest will be in order that plans can be made for the operation of Pardee Dam and for the schedule at the powerhouse. So men go into the mountain wilderness on skis and snowshoes to measure the snow and weigh it. Measuring tells how much snow there is, and weighing tells how much water it contains, so that by the end of the snow season, the engineers know very accurately how much water will run off by the middle of the following summer. Most of us never see the lovely winter scenes where nature turns the world into a fairyland of wonder. Trees standing like white sentinels, the ground deeply covered with feathery white banks, a brooding silence over all. Nature pauses here between the autumn and the spring, and for a few short months, the snow lies deeply packed, awaiting the inevitable swing of the magic cycle of the seasons. Step by step, as though reluctant to release her treasures, nature turns flakes of snow into drops of water, and many a little brook awakens from its frozen sleep and moves to fulfill its destiny. Mountain streams, responding to the spring sun, gather the water and form the beautiful Mokelumne River. Through the magic of modern engineering, we tap this distant mountain stream every time we turn the faucet in our house. How much water is flowing in the river? Any sudden rise or fall will be automatically recorded by a radio device on the Big Bar Bridge, which sends messages to the engineers many miles away. The exact quantity of water which the river carries can be determined through a device known as a current meter, which is lowered into the river from a cable above. The river is now coming under control. Never again will it know the wild, free days of old when it plunged downward unhindered to the sea. From now on, the Mokelumne River must render a service to man. People 100 miles away are thirsting for the clear waters which it has gathered from the towering mountains far behind. Through sunrise and sunset, by day and by night, the river moves to its appointed task. Pardee Dam, a great concrete structure, was built in a canyon 38 miles northeast of Stockton to hold back the river and form Pardee Reservoir, main impounding basin of the Mokelumne system. It is this barrier that first brings the river completely under control, creating an artificial lake holding 68 billion gallons. The dam is 358 feet high and 241 feet thick at the base, and the reservoir has an area of 2,250 acres. It is 94 miles from the East Bay City. Water can leave the reservoir by means of large pipes or sluiceways running through the bottom of the dam and thus reach the river below. Control valves regulate the amount of water passing through the dam. These are often kept open during times of flood flow in the river. The water can also leave by means of a spillway over which it pours when the level in the reservoir comes within 12 feet of the top of the dam. This is a safety device to ensure that water will never go over the dam. 850 feet long, it will carry several times as much water as has ever been known to flow in the Mokelumne River. After leaving the spillway, it passes down Mexican Gulch to rejoin the river. Water leaves the reservoir in this way only during years of heavy runoff. Most of the time, the flow of water in the river for the use of interests in the valley is maintained by releases through the power plant, which is equipped with 2 generators driven by turbines with a total capacity of 20,000 horsepower. Power is sold at the plant to the Pacific Gas and Electric Company. The income to the district in a normal year is about $400,000. In years of subnormal precipitation, the power schedule is curtailed, since the water supply must take precedence over everything else. Water intended for our use in the East Bay leaves the reservoir through an outlet tower, which connects with a 2-mile tunnel, the first unit of the Mokelumni Aqueduct. These aqueducts are our lifelines with the mountain supply, in operation every day of the year, transmitting the water 94 miles from Pardee Reservoir to our local distribution system. The steel pipes, for most of their length, are nearly 5.5 feet in diameter. Like silver threads, they make their way across the delta, bringing over 90 million gallons a day by gravity alone. With these pumping plants at Bixler and Walnut Creek in operation, the aqueducts can deliver more than 140 million gallons daily. And in the future, this can be increased to over 200 million gallons by the addition of 2 more pumping plants. Our assurance that water, and plenty of it, will always be available when we need it. 3 times in their journey from the mountains to you, the pipelines pass under the San Joaquin River and its branches, and for many miles they're carried on trestles across the Delta peatland, bringing their precious cargo to our homes and factories. These great aqueducts were built at a cost of over $36 million. It is natural, therefore, that they should be carefully watched day and night to protect them from harm and to ensure that all of their ingenious mechanical devices are kept in perfect working condition. This is accomplished through an efficient system of patrols by means of which the lines and their structures are inspected every day. Routine inspection includes an examination of the expansion joint, located at frequent intervals along the sections above ground. There are hundreds of air valves which must be constantly tested to make sure they're in perfect operating condition. These valves enable the aqueduct to breathe as though they were living things. If there should be a sudden break in the lines, or if they are to be emptied for inspection or repair, the valves must open and let in the air to prevent a vacuum which would collapse the pipes. When the lines are being refilled, the valves must open to let the air out and prevent an airlock at the high places. We have seen how the water is gathered from the mountains, stored in Pardee Reservoir, and transmitted through the aqueduct. Now let's follow it through the various steps it must take to reach the faucets of the consumers. Upon arrival in the district, the water can either be filtered at once, or it can be placed in one of the terminal reservoirs, such as San Pablo. This is one of the large local storage basins holding over 14 billion gallons. Lafayette is the smallest of the terminal reservoirs and is situated about a mile west of the town of Lafayette. Its water can be made available to all parts of the district if required. Upper San Leandro Reservoir is in the hills back of San Leandro. It receives water also from the Mokelumne Aqueducts by means of a pipeline through which water is pumped from the Lafayette pumping station. It holds 13.5 billion gallons, and its supply reaches the distribution system through a tunnel which conveys it to the Upper San Leandro filter plant on Mountain Boulevard in East Oakland. This is probably the most scenic of all the district's local properties. And the road which follows the hills above the lake is one of the favored drives of the Bay region. Chabot was the first important reservoir to serve the city of Oakland. It was built in 1875 and has been in continuous use ever since. It holds a little over 4 billion gallons and is the only one of the reservoirs that can deliver its supply without passing it through a long tunnel. This makes it of the utmost value in case of an extreme emergency, which might put some of the tunnels from other reservoirs out of service. All terminal reservoirs are protected with spillways, which prevent rising water from passing over the top of the dam. Every drop of water served by the district passes through a complete process of filtration, and the district has 5 plants which are capable of producing all of the filtered water required. This is the Upper San Leandro plant. The Orinda plant is the largest of the 5 plants. It receives water directly from the aqueducts, and due to its elevation, is able to serve a large part of the distribution system without pumping. In a filter plant, water passes through a maze of pipes, all controlled by valves, so that one man standing at a control panel can regulate all the operations of the filter plant during the 8 hours that he is on duty. Men in white are constantly on guard day and night to protect the public health. They carry on their scientific work in 2 district laboratories, where tests are made at frequent intervals to determine the exact condition of the water. Since water is gathered from a number of places and stored in various reservoirs, it is not always uniform in quality when it comes to the filter plant, but it must be uniformly safe, clear, and of the finest quality when it leaves the plant. The laboratory technician knows that the water which is entering the distribution mains is free from the bacteria which in the old days caused epidemics of waterborne diseases. The standard of purity set by the district is far above the standard demanded by the United States Health Service. You can drink and you don't need to worry. To give us a clear understanding of how water is purified, the district has built a miniature filter plant. Water which has been stored in a reservoir loses some of its oxygen and may pick up odors and an unpleasant taste. The first step in filtration is aeration. This is accomplished by spraying the water high into the air, thus restoring its lost oxygen and improving its taste. From here, it is conveyed by pipes to another basin where alum is added. Alum is used to help clear the water. There's always some sediment, and the addition of alum causes the particles to stick together. The water with the alum added has to be agitated to cause the bits of sediment to coagulate or form masses, which can be easily settled out in the sedimentation basin. This takes place in the miniature plant exactly as it does in the regular plants which supply our filtered water. Paddles are revolved slowly in the basin. As the water is kept in motion, the alum comes in contact with the bits of sediment, causing them to coagulate into floating pieces which are large enough to be visible to the eye. The water stays in these basins from 10 to 20 minutes, with the paddles going round and round. By that time, all the particles have been gathered into what is termed a flock, and the water is then ready to take a little journey to the adjoining sedimentation basins where the clearing process is continued. Here the water remains almost stationary for about 3 hours, while the coagulated particles sink slowly to the bottom as we see here. 85% of all the foreign matter is removed in this process of sedimentation. Now the water must be filtered to remove the small amount of sediment that still remains. Filtering water simply means passing it through sand and gravel to strain out impurities. After water has been cleared in the sedimentation basin, it flows on to the filter beds. Slowly it percolates downward through the sand and gravel. When it reaches the bottom, it passes out through a network of pipes and flows off to one of the distribution reservoirs and thence into the mains which carry it to the faucets of the consumers. A filter bed is a rectangular basin 10 feet deep, having an area of 600 square feet, with a network of small perforated pipes at the bottom. Resting on the pipes is a layer of gravel 20 inches deep, and above the gravel there is a layer of 30 inches of fine beach sand. When the sands become filled with sediment taken from the water, the flow is reversed so the filters can be washed. The water seemed to be clean after it had been settled in the sedimentation basins, but notice the amount of dirt that has been removed by the filters. No, this wash water does not enter the distribution system. The final act in the process of purification is the addition of a minute quantity of chlorine gas. This goes into the water after it has been passed through the filters and just before it enters the distribution system. Spreading all through the water, the chlorine kills every germ that is dangerous to human life. The routing of the water through the filter plant is accomplished by this complex system of pipes and valves that controls every stage of purification. Now the sparkling clear water is ready for the distribution system. Here, in an overflow weir at the Orinda filter plant near the Orinda Country Club, the water falls in a glittering cascade into the 3-mile Claremont Tunnel, which will carry it to the Claremont pumping plant near the head of Chabot Road in Oakland. From here, water can flow east and west to the Sequoia and Wildcat aqueducts to serve a large territory by gravity. But this point is only 340 feet above the bay, and a great many people live at higher elevations in the hills, so a considerable quantity of water has to be lifted by pumps and placed in tanks and distribution reservoirs, the highest of which is 1,500 feet above the bay. For example, in the Piedmont area, the first lift to Piedmont No. 1 Reservoir puts the water at an elevation of 772 feet above the bay. Now it can reach many more consumers by gravity, but it must be lifted again to reach those who live still higher. The pumps do their work without human attention, turning themselves on and off in accordance with the demand from the reservoirs above them, lifting water to the highest points where human beings have chosen to make their homes. Higher and higher it goes, bringing comfort, convenience, and fire protection to thousands of citizens. From the reservoir, the water flows by gravity to serve the homes below. The Berkeley View Reservoir holds 1 million gallons at an elevation of 1,300 feet, which means plenty of water and good pressure for North Berkeley. The larger distribution reservoirs are at lower elevations. Piedmont No. 1 and No. 2 look like glistening blue jewels in a setting of East Bay homes. Homes that could not exist without the assurance of abundant water from our carefully planned distribution system. Central Reservoir in East Oakland is the largest of the distribution reservoirs and can serve all of the lower communities from Richmond to San Lorenzo. Here in the midst of the city is a lake of 149 million gallons of filtered water. A large part of Berkeley receives its supply from Berryman Reservoir at an elevation of 500 feet and holds 23 million gallons of water. Constant patrolling of the watershed is accomplished by the use of radio-directed jeeps and other mobile equipment, traveling continually through the backcountry to see that proper sanitary conditions are maintained and to deal with any fires that may start on district lands or adjoining private lands. The most modern mechanized equipment available is assigned this vital role of protection. Many new homes are being built, and the district must keep pace in providing new service. At the corporation yard, pipe of varying sizes is always in storage, ready to be hauled to the job as required. The pipes range up to transmission lines of more than 5 feet in diameter. The system is in a state of constant change. Old pipes are wearing out. New districts need new pipes, and some of the older districts have been growing and require larger pipes to bring improved service. The district carries on a continuous program of pipe laying to keep up with community growth. Where plenty of good water is always available, the people will build great public institutions, such as the University of California. Great centers of commerce and industry will develop as the population enjoys a healthy and steady growth. The East Bay area depends upon great industries for much of its prosperity, and the industries depend upon the district for a never-failing supply of the finest water in the West. Among these manufacturing plants are many which demand a water low in mineral content, and our soft water has therefore been an important factor in industrial development. Food and glass and flowers and building materials, an endless array of products flows every day from these East Bay factories, bringing the payrolls that give our people a better standard of living. And in this fascinating drama, water is always playing its vital but unseen part. Water has many uses, none more important than putting out fires. The danger of any great destruction is lessened if the firemen can hook their hoses to hydrants and be sure of an unlimited supply of water. Whether the fire is large or small, it doesn't stand much chance, but an East Bay Fire Department and the Mokelumi water system get together, and insurance rates are lower because of this protection. There's nothing quite like this to take off the grime. Baby's bath, so nice and soft that it doesn't require much soap. When he gets a bit older, he'll enjoy this, one of the best ways you can think of to use water. No better way to quench your thirst. And Pal here thinks so too. Gardens are more beautiful and homes safer and more convenient because there's always plenty of pure, clear water. We have seen how water, supplied from distant mountain sources, is brought to our community, purified, and delivered to our homes and factories through the facilities of the East Bay Municipal Utility District, which, by the miracle of modern engineering, maintains in plentiful supply our water lifeline at the turn of the faucet.